All right, this is the introduction to hypothesis tests, and we're going to go through pages 125 through 127. Please pay careful attention to this video. We're going to go through a lot of different topics that are a lot of different definitions that we did not go through in detail in class. Some of them will be left to further times, but we are going to hit a lot in this. So first off, you've heard the word hypothesis in your science class, I'm sure. And in statistics, hypothesis is an assumption about a population parameter. And the assumption or the theory may or may not be true, but it is a claim. Typically, we refer to it as the current state of affairs. It's the status quo. It's what we've believed for some time. All right, it's already what's been in place. All right, so what is hypothesis test? It's the formal procedure used, and it says to accept or reject, but we don't like the word accept. So it's used to retain or reject a statistical hypothesis. We prefer, instead of even retain, although retain is good, we fail to reject or we reject a statistical hypothesis. In other words, we're making a yes-no decision about the plausibility of the claim. Is it false or isn't it? If the data is consistent with the model or with the claim, then it supports it, but it never proves it. So one thing in hypothesis testing is we never go out and prove the claim. We never go out and prove it. We either find enough evidence to reject it, or we're forced to retain it because we failed to reject it. In other words, we couldn't disprove it. All right? And it's a lot like a jury trial, because in a jury trial, we have an assumption, and the assumption is of innocence. That would be known as, in statistics, as our hypothesis, and specifically as our null hypothesis. And it is, our null hypothesis is shown by an HO. And in a jury trial, the assumption is that they are innocent. All right? And then ultimately what happens is the prosecution gathers facts to determine against innocence. It sits there and go, hey, we have this against innocence. We have this against innocence. And ultimately, at the very end, we decide whether or not there was enough evidence to disregard innocence and say, you know what, they are guilty. However, at the end, we do not say, if we don't have enough evidence, we go, you know what, there's still some doubt. If there's still some doubt, we don't say they're innocent, we say they are not guilty. Well, in statistics, we either reject the null, we reject the claim, or we fail to reject it. We never get to say we prove the claim. We don't gather evidence to prove the claim. I think we can say that we've already addressed most of this. How do we know when we've done that? Well, when we do that, we do it by probability. And that's basically our p-value. Now, you've already been calculating a p-value. We just didn't tell you that's what it was. And in statistics, the p-value is a conditional probability and gives a likelihood we'd get a test statistic as extreme or more extreme than the original claim. Now, I'm going to go and explain that a little further in this video. I'll go through that a little more and make a little more sense. But if we calculate a probability of, let's just say 3%, what a p-value would say was, given that the original claim is true, there's a 3% chance that we would calculate a test statistic as extreme or more extreme in favor of the alternative hypothesis by random chance alone. In other words, by random chance, how likely are we to get a test statistic this extreme or a p-value this small? The smaller the p-value, the more likely we are to reject. So if we have a very small p-value, if we have a low p-value, we're going to reject the null hypothesis. If we have a large p-value, then we will fail to reject. We didn't prove the hypothesis, we just failed to reject it. All right? And I guess the big question is, when you're running a hypothesis test, is can we say that this data plausibly happened by random chance alone? And so that means you're going to ultimately have to choose some p-value. If you sit there, and most of the time, we choose a p-value of about 0.05. It's like, you know what, by random chance alone, if it happens by 5%, I'm not going to believe the initial claim, I'm going to reject it. There are times we need a much smaller p-value, maybe 1%. There are other times it'll be 10%. That said, we will choose a value before we ever run the test to determine whether or not to set the standard. Okay, so we will make that choice long beforehand to make that standard. And once again, a p-value, if we calculated a p-value of 3%, there's a 3% chance we get something this extreme in favor of the alternative when in fact the original claim is true. In other words, it's kind of the admission of a mistake. It's like there's 3% chance, and that's why we tend to set these things around 5% or 1%, sometimes larger, but usually the problem will tell you, but if it doesn't tell you, you're going to use a 5%. All right, and anything smaller than that, small p-values, I guess the big thing is if you get a small p-value, you reject. If you get a large p-value, you fail to reject. All right. Obviously, in a trial, we have a presumption of innocence, and the burden is on the prosecution to gather enough data, all right, to gather enough evidence. And there'll be some evidence in favor of the defendant and some evidence against the defendant. And that's why we will never be able to say with 100% that we're able to 100% reject it. Because there's some evidence that says, you know what, it looks like they're not guilty, but there's so much saying that they are guilty, we believe they are guilty. Or you can sit there and go, there's not enough to say that they're guilty. Well, that's the same with the hypothesis test. It's like, well, we have some data that suggests the original claim is true, but we have a ton that says it's not, so we're going to reject. Or maybe we say there's not enough to say that we're going to reject. I've been talking about the alternative. We express the alternative hypothesis as HA. And in a jury trial, the null, the hypothesis, the initial hypothesis would be expressed as HO, and that it would be that they are innocent. So in jury trial, the claim HO would be that they are innocent. The alternative hypothesis would be that they are guilty. So if you reject the null, you're forced to believe that, or you switch your belief to saying that they are guilty. There are 4 basic steps to the hypothesis test. One is to state the hypothesis. And by the way, recipe card will break this down very, very specifically. The null is a statement of HO equals. So that's your null hypothesis. Your alternative hypothesis can be stated one of 3 ways. And by the way, I guess I should make one more comment about the null before I move forward. It will always be an equal statement. Since we're talking about means now, it'll be mu equals, all right? But it'll always be an equal statement. The alternative will be either a less than, greater than, or a not equal to, all right? Less than a parameter, greater than a parameter, or not equal to. And we'll practice writing those when we actually get to the problem in the next video. The next thing is we need to give the formula and list the conditions. Not a lot of fun, but we have to write those conditions, and you need to write the formula down. The mechanics, we're going to plug into the equation, calculate a test statistic, and the p-value. Once we get to the p-value, we'll go, hey, it was this likely or unlikely to get a sample this extreme by random chance. And once again, a p-value is telling you how likely you are to get something by random chance alone. And because if it goes, you know what, it happens 25% of the time, that's not common, but it's not really that rare. So we want something really rare in order to reject the null. And typically we state that at about an alpha level at when we get a p-value less than 0.05. So then we get to our conclusion part, and we're going to say whether we reject or fail to reject a null. We always need to state it in context, and the conclusion should tell us what we're going to do, all right? And that will be in terms of the alternative. So that would be in terms of HA. Now, we are going to have a template on what to write, so it's not that big of a deal, but you need to practice that. So one is drop down, because I believe you can read this top part on your own, and we've already talked about it a great deal. But we're going to talk about the alternative hypothesis because we have several definitions that go with it. We have, first off, we have a mu not equal. First off, because it's a not equal, that is known as a two-tail hypothesis. So if I have a not equal, and let's just say I happen to have a sample of 40, which means since we're working with a t-statistic, I'd have 39 degrees of freedom. And let's just say that we are going to set alpha equal to 0.05. And you go, what's alpha? Well, first off, alpha is known as the rejection zone. It's the amount of area we have in the tails. Sometimes we even refer to it as the level of significance. And I'm not going to write that out, but the level of S, the level of significance. I guess I'd probably write SIG. And if I notice I have 0.5, if I'm in this 0.59 range, I'm not rejecting the null. However, if I add those two values up, I end up getting 0.025. That's my area in the tails. And if I get anything in this area, I'm not rejecting. But if my area is out here, I do reject. So if I run the test and my p-value is less than 0.05, I'm going to reject. And basically by setting it at 0.05, I'm saying I don't mind being wrong 5% of the time. And you're like, I don't really like the sound of that. And I'm like, well, I think you're happier with it than you may know, because if you make a 95 on the test, you're generally pretty happy about that. And basically that was saying you were wrong 5% of the time. So we generally are okay with an alpha of 0.05. There are times that it's not okay, but you're probably wondering where I got these two values. These are my t values, or t statistics, and they're also known as a critical value. And if I get a t value less than negative 2.0226, if I get a t value less than that, I'm going to reject the null. And if I get a t value greater than this, I'm going to reject the null. And remember, the t is centered at 0. And so anything as extreme as 2.0226 and further to the right, I reject. Anything less than negative 2.022 I'm going to reject. Or I can look at my p-value and compare it to 0.05. And please remember, we're going to be comparing p-values to the alpha level. Now, real quickly, I'm going to show you where I got that test statistic from. So second vars, inverse t, parenthesis, 1 minus 0.95 divided by 2. And I'm dividing it by 2, and I'm doing the 1 minus because I'm working with a two-tail. My degrees of freedom was 40 minus 1, or just 39. And when I do that, I end up getting a test statistic, or a critical value of negative 2.0226. We don't use critical values that frequently anymore. We generally talk about alpha and p-values. But if we had a test statistic, if we came up and ran our test, and we calculated our t using t equals x bar minus mu s divided by square root of n, if I came up with, after I ran that, a t that was less than negative 2.0226, I would reject the null. I would reject HO. On the other hand, if I calculated a t statistics that was greater than 2.0226, I would also reject a null. So after I run this equation, if my value is greater than this, I reject. If it's less than this, I reject. Or if I get a probability that's less than alpha, I reject. Either one of those two things, okay? All right, the next one. We're going to talk about a one-tail. In this case, we're going to talk about a one-tail upper tail, all right? And you have two types of one-tail tests. You have an upper tail or lower tail. We're going to go ahead and keep our sample at size 40, which means we have degrees of freedom of 39, and we have an alpha of 0.05. If we get a probability, a test probability less than 0.05, we reject. Now, this is my critical value number. Again, it's a t statistics centered on 0. And you're probably wondering where I got that from. Well, remember the calculator works from left to right. So second vars, inverse t, and I'm going to use 0.95, degrees of freedom, 39. And I end up getting 1.6848. So if I go ahead and I run t equals x bar minus mu s divided by the square root of n, if I run that and I get a test statistic greater, if I get a t value greater than 1.6848, then I need to reject the null. The probability that's associated with it, if I get a probability that's smaller than 0.05, in other words, smaller than my alpha, if my p-value is smaller than I alpha, I reject. Okay, once again, if I move any value greater than 1.6848, I'm rejecting, or a p-value less than 0.05. And once again, the calculator will put that information together for us. Finally, the lower tail. With the lower tail, we're working with a less than, and our alternative is going to be something that looks like this. Our null is always going to be the equal. We've gone ahead and kept things at a sample of size 40, with which means we have degrees of freedom of 39, and all of our area is at 0.05, so our alpha level is 0.05. Our critical value is set here at negative 1.6848, and we're centered at 0 because we're working with a t distribution. And once again, this just came by second vars, inverse t, 0.05, and I end up getting negative 1.6848. All right, negative 1.6848. So after I run my t equals x bar minus mu s divided by the square root of n, if my test statistic, if my t that I calculate is lower than negative 1.6848, I'm rejecting. Simple as that. Or I can look at my p-value, the probability, and if my probability happens to be less than my alpha level that I set at 0.05, then I'm rejecting. And please don't forget, alpha is also known as your level of significance. So one last thing, we reject if the p-value is less than alpha, and we fail to reject if the p-value is greater than alpha. And it's usually better to work with p-values. Also, alpha is the area in the tail, all right? Alpha is the area in the tail. This is extremely important that you understand alpha, and you also need to really understand when we reject. We'll be working with p-value enough that over time that's going to come together for you. And generally speaking, because of the calculator, we don't use critical value testing as much. So the critical value, nice to know, not as important now. It was very important when I was in school when we didn't have the calculator, but it's not as important now, although every now and then a test question will appear about that. All right, thank you for listening to that. A lot of this will become more clear as we work through a couple of hypothesis tests.